Thank you, Sebastian. First of all, I would like to thank everyone joining us in this webinar. It's really a pleasure for us to be able to share what we presented in this paper and spread a little bit the latest developments in regarding EV charging infrastructure. So we'll pick up the presentations and focus more on the topologies of power converters used for all these different kinds of families of EV charging stations that Sebastian already talked about. For the purpose of this part of the presentation, we are going to group them into three categories. One, which Sebastian already mentioned, which are the onboard chargers, in which the whole electronic circuit during the charging of the battery is on board of the vehicle. And because of that, those tend to be smaller in size, and hence they charge slower as well. They are rated at a lower power level. So you can see here they can range from 1.9 to 22 kilowatts, and depending on the topology, the circuit, and the car. And then we will go into the integrated chargers. The integrated chargers have the difference between they are also on board, but the difference between the onboard chargers that we spoke before is that this one have a dedicated function, while the integrated charger have two functions basically. The integrated charger works not just for charging, but it also is used in part to drive the vehicle. So we are going to repurpose part of the electronics used to drive the motor to actually use it to charge the battery when the car is not moving. And then we will move on to the last category, which are the offboard chargers, in which all the electronics is outside of the vehicle, and because of that they can be larger in size and hence have a higher power rating and therefore charge the batteries in a faster time, and that's why they are also known as fast chargers. Usually the first category, the onboard chargers, are connected to AC grids. The same is the case for the integrated charger, although there are some that have a dual connection to AC and DC. And finally, the offboard chargers are usually connected directly to DC. What I mean by that is they are, of course, connected to the grid, but they tap directly into the battery of the vehicle. So here you can see a summary of different commercial topologies, and we are going to now discuss a little bit of each one, and then we'll see how clear trends emerge from what the industry is doing in terms of modularity, in terms of kinds of semiconductor technology, and so on and so on. So let's start with the onboard chargers first. This one is the one by Chevy Bolt. So this is on the Chevy Bolt vehicle. This is a second generation OBC, onboard charger. And as you can see, this is a single phase connection. So this can connect to the outlet of electrical outlet at your house. And therefore, it does not provide that much power. And here you can see that it gets up to 3.6 kilowatts. So it's kind of 2 times the power level that you have in a hair dryer or a toaster or any home appliance. And this is also typical, the maximum rating that you can get when you connect to a single phase system. In this case, it's also with a passive rectifier, although it uses a DC-DC stage that provides power factor correction to have sinusoidal currents from the grid. And then you have the isolation stage that Sebastian talked about. And because this is on board the vehicle, we have to take into consideration power density. This means try to have it packed in the smallest package as possible, so you don't use volume and weight of the vehicle. And therefore, the preferred use is to use high frequency transformers. This allows to reduce the size of the magnetic components and therefore have higher power density. In this case, they're using an LLC resonant full bridge converter, and then you have a rectifier that rectifies the voltage after the high frequency transformer to supply the power to the battery. This is the one that already was in the previous slides by Sebastian, but I just wanted to highlight now here the topology part of it. This now is a 3-phase connection, and therefore it can reach up to 11 kilowatts. So this would require, if you want to use this at home, an additional kind of connector system, so you can actually have a 3-phase connection. This can be also connected to other charging ports in supermarkets and other places in around the city. And they can operate actually as a single phase or a three-phase system. So the power range goes from a few kilowatts to 11 kilowatts. It's a very similar topology to the one I showed before. So it uses single phase rectifiers for each of the phases using power factor correction. And one thing that here you can already see becoming a trend is that most of the chargers that we will see are employing this high frequency isolation uh, transformers. So in order to reduce the size and increase the power density, and also because of this, there is a limit that of the power that one of the single units can drive, and therefore you start paralleling these converters in a way that you can handle more power. And this can also bring benefits in terms of reducing the magnetic components, because you don't control all these converters with frequencies that are in phase, but you do a kind of an interleaved connection in such a way that you reduce current ripples, and this can also further reduce the sizes of the in the inductive components and magnetic components of the circuit, further reducing the size of your charger. Um, so you can see that because of these high frequency isolation stages, maximum efficiencies go up to 95, 96%, because you have extra losses by going into these high switching frequencies, and also by using these isolation transformers. So this is a way to go, just in order to be able to fit these chargers on board. This is the case of the Tesla Model 3 and Model Y. So this is a very common charger in many vehicles, since Tesla has a large market share around the world in electric vehicles. And here again, you can see that it uses a single phase and three-phase active power rectifiers. So you can reach actually up to 22 kilowatts. This is at the higher end what you can get for onboard chargers in electric vehicles today. It is a fully controlled rectifier in this case, but it doesn't provide still bidirectional power flow because of this passive diodes at the end. So you cannot this cannot do or perform vehicle to grid because you cannot transfer power from the battery to the grid, as we will see. That is the case for other topologies, as we will see later on. Which is actually this one here. This one is from Ella, and this one uses GaN semiconductors, so gallium nitride semiconductors, which are wide bandgap semiconductors. These allow to switch way faster, and therefore they have lower losses. And here you can see how the efficiency increases up to 97%. Again, it's using single phase unfolding rectifiers. This is an active controlled rectifier, it's not with diodes. But you use one for each phase of the three-phase connection. It can also operate as a single-phase rectifier or three-phase, and that's why it gets to 22 kilowatts. The high-frequency components, meaning by this the gallium nitride semiconductors, are used for the high-frequency isolation stage, which is the one that requires higher switching frequencies, and this allows to further reduce the size of the magnetic components of the converter, which is a nice benefit. This one also uses the same kind of semiconductors. This is the reference design by GaN Systems, which is a brand that commercializes GaN semiconductors. In this case, they are providing a reference design for a different kind of topology, which is a 311 flying capacitor converter. So this converter, compared to the previous one, which generates 2 voltage levels at the AC side, this one generates 3 voltage levels at the AC side. This has some benefits in terms of power quality that also helps to reduce the magnetic components of the circuit. It also can work at lower switching frequencies, increasing the efficiency. And again, by using these advanced semiconductors, there are some benefits in terms of losses. As you can see, this one reaches higher efficiency rates compared to the previous solutions that were shown before. But again, this one is again using high frequency isolation. The main difference between this topology and the previous ones is that the previous ones draw less power, and I'll just go back, and therefore you need several of these modules in parallel to reach the 22 kilowatts. level. But in this case, because these are multi-level converters have a way of reducing the voltage stress across the semiconductors, and this allows you to draw more power using a single unit, and therefore here you don't see that they are used in modular connection between each other. And then we have this one by Innoelectric, and this one is using silicon carbide semiconductors. So this is another type of semiconductors. It's also fast switching semiconductor compared to traditional silicon carbide, traditional silicon semiconductors. But the interesting feature of this topology shown here is that the output is made in such a way that instead of just having these modules connected in parallel to reach more power levels, they actually can be also connected in series. And by connecting them in series, you can actually reach higher voltages at the output. And here's where you can see that this one can cater either voltages for batteries around 400, operating at 400 volts or 800 volts. And this can be done using the switching matrix connect at the output, in which you can connect these two outputs in series for 800 volt batteries, or in parallel for 400 volt batteries. So that's kind of the advantage of this topology over here. Can be used in different kinds of architectures of electric vehicles. So those were the onboard chargers. Now we're going to move on to integrated charger topologies. So integrated charger topologies, like I mentioned before, are the ones that make use of the existing electronics in the powertrain of the vehicle. So that normally uses, when driving the vehicle, drives the power from the battery to the motor, or from the motor to the battery when it's braking, when it's doing regenerative braking. And because of this bidirectional power flow, when the vehicle is not running, you could repurpose part of those electronics to actually use it for the charging system. And because it's not a dedicated charger, the rating of these converters is the rating of the car, basically, of the powertrain. So then they can draw much more power from the grid compared to onboard chargers. So here is a case of the Renault Chameleon. And in this case, here is a traditional powertrain. It's using a traction inverter, a two-level, three-phase inverter to draw power from the battery to the motor. But when you connect this to the grid for charging, it uses an auxiliary rectifier circuit, and then you use basically the windings of the machine, the windings of the motor, as inductors for the converter. So in this case, we won't use this as an inverter anymore. We are going to use this as a DC-DC converter, actually as a boost converters, and these would be the boost inductors to increase the voltage from the grid to the battery. And here you can see that the power levels that it can reach is higher, because this is now rated at the rating of the powertrain of the vehicle. This one is by Siemens and Valeo. It's a reversible charger. Basically, this means that it can work as a motor drive and as a charger. In this case, it's also vehicle to grid capable. The previous one, I'll go back, because this is unidirectional in power flow. This cannot perform from vehicle to grid power flow. But this is not the case in this one, in which it is possible. So here now you're using basically the inverter as a active rectifier, and then the DC-DC stage that has isolation, you're using to decouple the voltage of this DC voltage here and the battery one. So this one is actually performing the battery charging process. This one is just rectifying. So it's a two-stage conversion system over here, and as you can see, it's bidirectional in nature, because when you are driving the motor, you are actually drawing power from the battery to the motor. So this DC-DC converter is bidirectional in nature. Then this one is from Continental. It's called the All Charge System. It's similar to the first one I mentioned. I showed in Valeo in the sense that it is not bidirectional capable. So this is not vehicle to grid capable, because you have a passive rectifier at the input, and then you are using the traction inverter as a interleaved 3-channel boost converter. The difference between the values that this one does have a DC-DC stage with high frequency isolation, And depending on how you control the switches, you can actually have a DC connection to this one. So this can be operated with AC or DC inputs, not just AC inputs. And because of this, you can actually charge at really high power rates, which reach up to 350 kilowatts. It can also cater batteries from 400 to 800 volts because of the flexibility given by this DC-DC stage, depending on the windings ratio of your transformer over here. And with that, we go into the biggest category, I would say, in terms of different kinds of commercial chargers, which are the off-board chargers, also known as DC fast chargers, because you connect directly into DC. And here we will start with the more traditional ones, the earlier ones, still operating though very successfully. This one is the ABB Terra 54. It uses single phase rectifiers. So you need one per phase, and then you need a lot of these different power building blocks, power electronic building blocks, also known as PEB, in parallel to reach the power output. So they are rated at 10 kilowatts each. You need 5 of those to reach 50 kilowatts, as shown over here. The interesting part of this converter is that you have a connection at the later stage of your charger, in which you can operate as a dual function, in dual operation, either as a full bridge or as a half bridge. So you can actually double the voltage or cut the voltage in half. And this allows you to cater for 400 volts and 800 volts vehicles. It's again, this one has a passive front end, so it's not bidirectional. It cannot work as for vehicle to grid. This one can, so this one is fully bidirectional in power flow, as you can see by the active switches at both sides. It uses a traditional 2-level voltage source rectifier. It uses 3 PEPs, each one of 50 kilowatts to reach the 150 kilowatt total. And it seems like, it looks like a back-to-back configuration, but in fact, this one is actually used as AC-DC, but this one is used as DC-DC. This one is operating instead of as an inverter. It's actually operated as a DC-DC converter, used by working it as a 3-channel interleaved buck converter. This one is a Tesla Supercharger 2. We're going back to unidirectional rectifier in this case, due to the single phase rectifier here made of diodes. So that's why we cannot have power flow into the grid. The interesting thing of this one is that they are repurposing the onboard charger unit. So the single phase onboard charging unit they have for their vehicles, and adding 3 of those to make it 3-phase, and then 13 of those to reach the power level that you need for the charger. So it's basically the same topology I showed you at the beginning for the onboard chargers, but now reconfigured and repurposed for a DC fast charging station. Then we have, this one is by Porsche. The main difference between this one and all the ones we have seen here before is that it uses a low frequency transformer for the galvanic isolation between the grid and the batteries. And it's also using a passive front end, so no bidirectional power flow capable. But because this the 2 secondaries have provide 2 channels of isolated voltages and currents, we can use then this converter over here and this converter over here in a way that we can connect them in series or in parallel at the output using this switching matrix. So this allows to connect the charger to 400 volt batteries or 800 volt battery standards, as you can see over here. The delta Y connection generates a 12 pulse rectifier, so in this way you can get rid of low order frequency harmonics, which is good in terms of power quality and complying with grid codes for this power level. So yeah, this is an interesting topology in this sense. And this is another one by the same company, also using the same kind of input, but in this case now it's using a Vienna rectifier, as you can see over here. which is a different kind of rectifier capable of handling more power, and directly there is one channel connected to one VNA rectifier, another channel, the Y connection to the other one. And because the isolation of these two power channels, we can also again connect them at output in parallel or in series, depending on how you configure the switching matrix over here. Um, the VNR rectifier can operate at higher voltages, and therefore we use now a three-level buck converter. The three-level buck converter can reduce voltage inherently by two compared to the other one, allowing the voltage ranges that we require for the charging of the vehicle. Then this one is from Enercon. Maybe you are familiar with Enercon as a wind turbine manufacturer, and they have repurposed their power electronics to use it for charging purposes. So basically, they are using their traditional grid-connected rectifier systems, but now for charging purposes. But because of this, it has also embedded the grid services that are already in place for wind turbines. So they have already this incorporated in the product. And then this is followed by galvanically isolated high frequency um, converters, as you can see over here. It's with the passive output. So because of this, it's not bidirectional capable. And again, because of all the different channels, they are galvanically isolated. We can now, with the switching matrix, connect them in parallel or in series, depending if we want 400 volts or 800 volts batteries. And then finally, uh, this is a demonstrator. So this is, I believe it's not commercial. Maybe it is by now, but the best of our knowledge, this is a demonstrator in which Delta Electronics is proposing a solid state transformer rated at 400 kilowatts to actually not just connect a medium voltage DC AC grid to the batteries, but also have flexibility to connect other energy storage systems and include and also distributed generation plants like PV arrays and so forth to have a more flexible operation. So this one is intended for megawatt charging systems that in the long run. So the ones that Sebastian talked about working at higher power levels, in which you can integrate also energy storage systems to reduce consumption from the grid when you have peak charging periods in which you're demanding a lot of power from the grid. Then you can use it from this local battery array and then reduce stress on the grid. And this extra flexibility allow you to provide more services to the grid and more interaction to the grid, even when the converter is when there is no vehicle charging. Then you still have all these assets connected to the grid through this converter. So then you have basically distributed generation and distributed battery energy storage systems connected, and you are repurposing the same electronics for more uses, and there is therefore more business cases to make out of that instead of charging vehicles. So this is a little bit also one of the trends that we are seeing from many manufacturers trying to use the charging stations not just for charging, but providing other support services to the grid in order to have have a stronger business case to making these large charging stations rather than just charging vehicles. We know from time to time those charging stations are idle, not operating or doing much, and this is a way then to capitalize more on the investment. And with that, I pass on the presentation to Stefan.